Okay, so in today's lecture, we are going to introduce the third model. It's called LASSO. It's very popular. It's called it's like specifically for the sparse regression. So let's introduce something that is slightly different from regression for now, but you will see, and everything later they are deeply connected. So one of the things that is and very and helpful is something called feature selections. But why the feature selection is so important is very important. So why the feature selection is important is lies in these two things. First thing is we want our model to be efficient. For example, later on you will see our date and our and model and you could see the dimension of our weight could be very large. As large as 10 to the 7th. As the result, the training and the prediction could be very expensive. And it could be and the memory intense, and to run your code it could take hours, even days. And also, the way that we can handle that is we can assume this W is actually sparse. So that means many entries of this W, our weight is actually 0. And then if we can, if like most of, so the entries are 0, maybe only hundreds or thousands of entries out of 10 to the 7th are zeros. Our prediction computations only, depends on the numbers of non-zeros. So that means this yi is actually equal to wj and times of this hjxi, which is our features. And these are the features actually matters to our predictions. And most of the features are not important at all, and which corresponding to the zeros weight. And also this sparsity can help us to interpret our models, because if the feature is 0, that means this feature is not relevant, it's not important. So we can get rid of that. So and if feature has like non-zero values, and whether it's positive or negative, so at least it is relevant for predictions. If the weight is positive, that means it's positive, and a positive correlated to the target. If it is negative, it's negatively correlated to the target. So if we, this is one of the examples that we can see right here. So think about housing price, right? So this is a very important examples. If you plan to take my 593, there will be project on house and house pricing and predictions. And if you go to Redfin or Zillow, you can see certain houses has some like all the listings informations, including like lot size and whether it's single family or not, and what year is built and so on. It could be like hundreds, thousands of features. I think in 593, the features that you're going to work with is more than 2,000. That's a ridiculous amount of features. And the data you are going to work with is nearly 1 million. So that's a really large data set. And the issue is not all the features are relevant to predict the house price and at all. For example, whether it has a washer or dishes or microwave has very minor an effect to this and the house price predictions. So we can simply get rid of this. So those and features in red font, and it could be like it's more like relevant and features for our predictions. For example, this lot size, whether it's a single family and which year is built, last sold price, and then finished square feet, unfinished square feet, and so on. These are actually really important features, can significantly contribute to whether it's positive or negative to the house prices. But the issue is, for example, right here we pick 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 features we believe are important. But out of 2,000 features, how do we know these 9 features are important just from the data, right? So how do you know that? Like, can we find another like subset of 9 features is even more relevant to those 9 features that you choose? So what you can do is you can do exhaustive like approaches. So that means we can try all the subset, right? So this will be the most naive approach, and we can take the like all possible subset and perform the linear regression all of them. But the issue is this is nearly impossible. For example, if we have a D features, there will be in total of 2 to the D models. If D is 1,000, that would be like you take the and even like like to the end of universe to find out the all possible subsets. So that basically is computationally impossible to perform such all subset regressions. So there are some ways that you can do to simplify this. For example, you can start with a simple model, then iteratively add features that you think is most useful to fit. So this is something called greedy approach. And also this is it's very much like an heuristic. So for example, you can pick a dictionaries of features for H1, H2 to HD. They are all the features. For example, these are the 2,000 features of the like housing. So what you do is you start with an empty set of the features. Then you run your like regressions for the current set of features one by one and obtain the weight for each features. So basically you run the and the regressions with all like current and features that we have. Then you are going to pick the next best features such that this feature will give you the lowest training and testing errors if I add this feature in. So basically, we just assume we just want to add one feature. And with that one like additional feature, my testing error is like low. It's the lowest. So that means this feature is the and it contribute the most and it's most important. So that's why this will be our new set of the features. So this is everything is done very intuitively. So this is a greedy approach. So we can add the most important features one by one. And like we can do this recursive. And of course, we can do this in the backward way. So we start with a full model, we can iteratively remove features and with the least useful to fit, right? So this is basically says if we remove one features, it turns out my and my training or testing error like doesn't like change too much. That means it's not relevant. We can just get rid of this. So this is like backward, and the one that we just talked about is forward. In fact, scikit-learn has that kind of functions. It's on the feature selection can help you to do this kind of greedy search and automatically. And we can even combine this forward and backward steps. Forward algorithm, we can insert the steps to remove features is no longer important at all. And this, in fact, will be taught explicitly in detail in the 593 courses. And I will demonstrate some like important like examples. But there are two problems with these approaches. First, the greedy approach will not result in the optimal features. It's almost impossible to find out optimal features. And the issue, another issue is this is also quite expensive. This process, we need to go through all possible features one by one. If we have 2,000 features and for each like adding one feature, we have to like go through this like 2,000 features. that's ridiculously expensive. And particularly if you have a lot of features, this will be nearly impossible to finish. And also, there are some issues is when shall we stop, right? Hypothetically, that would be some of your training and testing area is low enough. But the question is, what do you mean by low enough, right? So, like, can you give a like definitively quantitative way to describe when you should stop? That would be a question to ask as well. Another way that we can do is we can take this ridge regressions, right? So, and we have talked about this, ridge regression in the last lecture. So basically, what we can do is we can and start with a full model with all possible features. If we include all possible features, we can almost guarantee to say they will have some overfitting issues. Then we are going to add this ridge regression term. So this is basically and the measure of the magnitude of the coefficients, and this is the regularization and like parameter. If we adding this and getting this lambda getting larger and larger, it will shrink some coefficient exactly to 0, right? And gradually it will like and going to be very small numbers. Then what you do is you are going to knock out certain features if the weight is like and the lower enough. Like you said, for example, like threshold, like say 0.1, if the weight is below the, if absolute value of the like weight is below 0.1, you say, okay, they are not important, I get rid of this. For those like, and weight is bigger than 0.1, that is, I consider is non-zero, and that means that would be the feature should be selected. So that sounds very reasonable, right? So, that's right. And we use the method we have a talk about on the ridge regressions. But the issue is, as I said, ridge regression can make coefficient to be small, but not exactly equal to 0. So, but we can, as I said, I can set the threshold, but sometimes it might have a big issues. There's some issue that we don't expect at all. For example, right here, so this is some examples. It's very realistic examples that we can just set some like small ridge coefficient to 0. For example, these are the corresponding weight of my one particularly rich and regressions result on this house pricing predictions. And you can see if we set the like threshold, and I want to remind you, if we want to set threshold, you have to set the positive and the negative because the weight could be positive, it could be negative. The only thing that is considered not important if the absolute value of the weight is less than certain values here. So basically, you can see these are not important right here. So that means we're going to get rid of these features. Instead we're going to keep this 5 of that, which is corresponding to square feet living, square feet lot, year built, and a year like renovated, and a waterfront. So, and of course, and this will be some features that is above certain threshold. But issue is, we see some like two features could be deeply related. And we see the number of bathroom here, we see the number of showers here. That's obviously if we have one shower, that's more likely and that shower will be in a bathroom. So these two features are highly correlated, right? So that means if we only include one feature, so that means if we get rid of this number of showers, it turns out this weight is significantly getting higher. So you can think about, it actually combines both the way together. So then the number of bathroom actually will go above this threshold. So that means if some features are highly correlated, this kind of like, and the thresholding techniques on the ridge regression is not good. Could be really, really bad idea. So that's why, and it's not a good idea to like threshold this ridge regressions. But the question is it possible that we can add the regularization that can directly lead to the sparsities? So this is something that we are looking for. Okay, so yes, that's possible. Okay, so let's go back to the math. Okay, so this is something called LASSO. So LASSO is it's called like least absolute shrinkage. And selection operator. So we have L here, A here, S here, S here, O here. So this will be LASSO. Okay, so that means, so this is the name. We were going to talk about what is the least absolute shrinkage means, what is the selection operator means. So so the key here, I mean, the goal is we want our parameter not just to be small, but to be sparse. So that means some component to be exactly equal to 0. Okay, so this is equivalent to say I want to minimize the L0 norm. So what does that mean is if we have and the 0 norm is if the value is non-zero, and I'm going to add 1 of that. And if that component is non-zero, I will add like 1 and to that. If it is 0, that will be 0. So this is equal to I from 1 to the D indication function of absolute value of each component is bigger than 0. So that means if it is 0, it has no contributions. If it is bigger than 0, you will add 1. The issue is this is not convex. And not differentiable. Both are really, really bad. I mean, if it is not convex, we can still find the gradient. We can do gradient descent. But the biggest issue is not even differentiable. So if it is not differentiable, this like basically there's no way that we can optimize that. So this is basically almost impossible to optimize. Okay, so here we go. So, and how can we approach to this? So we're going to using similar idea, but in this cases, we're going to using I'm still using the MAP estimation, but with a different prior. So we're going to use MAP estimation. And I want to remind you previously, we have this and like 0 mean Gaussian for my prior and for my parameters. Then we can have the and derive this MAP estimations. It's equivalent with the ridge regressions. But in this cases, I'm going to choose MAP estimations with something called a Laplace prior. So, and what does that mean is my prior is actually proportional to the multiplications for the following thing is exponential of minus lambda absolute values of wi. So I mean it actually is multiplications of bunch of exponential functions. And here I said the proportional because it's so there will be one like normalization constant, and actually to make sure this is normalized to be a probability. But this is something I mean in MAP, I mean it's always some constant because we need to take the logarithm. After we take the logarithm, I mean this constant just becomes 0. So this lambda here, right here, it's our regularization parameters. And if we have this prior, then the like posterior distributions of the condition on the data right here, it's equal to probability. I mean, it's proportional to probability of the conditional data and multiply the p of the w, which is the prior, right? So what we do is we take the and take the logarithm on both hand side and put the minus sign here. So minus logarithm it's equal to, I mean, we get rid of all these constant here, minus logarithm of the conditional probability minus of logarithm of pw. Okay. So this is, we have showed these things again. So I mean, this is nothing but negative log likelihood. Right here, the second one is basically lambda of one norm of my coefficient. So right here, is equal to the summation right from 1 to the d of wi. So this is the one norm. I mean, it's basically absolute values of each component. You sum them together. So this is something called L1 regularizations. And the reason that we call it, I mean, it's L1 regularization, it's compared to the Tikhonov or L2 regularization. I mean, so ridge regression is also called L2 regularizations because right here in L2 regularization, we're using the 2 norm and the square of the 2 norm. Here it's L1 regularization. We're just simply using the 1 norm right here. Right. So this gives you some motivation of the L1 and of the L1 norm right here. So and of course similarly we have like two and the two possible situation here is when lambda equal to 0, it is I mean, so let's just call it WL or an L1. This is just like precisely equal to the least square. So if lambda is positive infinity, then this is becomes all zeros. Right? So nothing, I mean everything is gone. If like lambda is in between, then we know this is, and this whole thing, I mean, in terms of one norm, it will be smaller than the least square norm in terms of one norm, but bigger equal than the zero. So one norm of my weight will be something in like and in between and roughly. Okay, so this is kind of like a good idea. Like it's very similar. If we actually implement that and solve this, you will see something like that. You will see something like this. So this is kind of interesting because in the ridge regression, if we actually plot this and I mean, this is something called regularization path. You actually need to do that in the homework. You can see if my regularization is small or even zero, every component is non-zero. And also all these weight, I mean, could be very large in terms of absolute values. As my lambda is getting bigger and bigger, then this weight is gradually decreases. And I want to emphasize all these weight will be precisely strictly non-zero. It's just like and getting smaller and smaller, but they are not precisely equal to zero. You are going to plot this out in your homework, something like that. So this is some plot that you should expect to. So you can see this curve is actually the weight for each features, right? With respect to my like L2 regularization parameters, lambda here. However, if we're using L1 instead, say if we can solve this optimization problem. So initially, if we have lambda equal to zero, this is the least square. If it is lambda, I mean, it's going to infinity, and this will be like zero here. But the difference is in the middle, is some feature actually just goes to zero and it stays zero. So what does that actually mean? It can goes to zero perfectly. I mean, so that indicate if I'm choosing my lambda right here, I only have two features. One feature is here, one feature is here. So this feature is probably the floors. This feature is probably the bathroom. So that means I only have a two feature that is non-zeros. Other two feature and other features that just precisely equal to zero if we choose this lambda, specifically this value here. Other than the ridge, I mean, so unlike the ridge regressions, I mean, the value will be small, but just remain non-zero. The LASSO L1 regularization can ensure at certain like lambda is between 0 to infinities, some feature and the weight for some feature is precisely to be zeros. And there will be some other features to be non-zeros. So this can guarantee the sparsity is here. Okay, so I will start here. So this is just a simple introduction to the LASSO. In the next part, I'm going to talk about why this is happening, why this L1 regularization can give sparse solutions, and also how can we use an optimization method to actually to solve I mean this problem numerically. Okay, stay tuned for the second part.